as well, knowing that there's going to be a special case with copper. See if you can figure out what it is. Feel free to talk to your neighbor. All right, so for nickel, you should end up with the argon in brackets plus 4s2 and 3d8. Remember, see how that works? Okay. And then for copper, where's my copper? Again, we're going to have the argon in brackets. We have 11 electrons to place in the remaining orbitals. We're going to have 4s1 and 3d10. And here in this case, that completely filled 3D subshell is more stable than having an extra electron in S to make it completely filled and a 9 in the 3D. So this is a more stable case. And as you go down the periodic table, down the rows, continue filling on. So for instance, for technetium, you would have the noble gas krypton in the row above. And then you would have, let's see, where are we? We're in position 10 from the right, so we'll have 5s2 and position 7, sorry, can't count, 4d5. Okay, questions on this? Yes?
How do we know if there's a special or not?
Yeah, so the special cases arise when you get the half-filled subshell and the completely filled subshell. So I'll have to check. I believe that molybdenum is another case, as is silver, but there are other interesting cases as well. Ruthenium has an interesting case. I just want you to kind of remember in general. That first row, other than copper and chromium, pretty straightforward. That didn't answer your question.
Yeah. Is that gonna be like on the test though, like knowing special?
I don't know. It's not really this semester's material, so I don't think it's going to come up. Just more of a reminder here. We're going to fill orbitals in a different way. We'll have to also recall our molecular orbital diagrams, and so in that case, we're going to have we'll be focusing more on that. That our chromium electron configuration in the elemental state, argon 4s1, 3d5. Originally we had 4s2, 3d8, so those s electrons will go away. Copper, we had 4s1, 3d10. We'll lose that s electron. Then, okay, so then we also need to think about oxidation of these metals, transition metals. Formation of ions, so loss of electrons to form the ions. So the good rule to remember is that the elements will lose outer s electrons before they'll lose the 3D, so 4s versus before 3D electrons. And so we can write out electron configurations for what we normally would see in terms of the ions present. There's be able to write the electron configuration to know how many electrons are going to be in the d orbitals. So chromium, we said previously, this is going to be able to form the 3+ ion. And so we'll remove 3 electrons. We're going to remove the s electron first, and then 2 of the d electrons. So we'll end up with an electron configuration of argon 3d3. So again, we lose the s electron first, and then the d electrons. For nickel, we'll often see a 2+. And for copper, we'll also often see a 2+. There are other 6+ state. Hexavalent chromium, if you've heard about hexavalent chromium, that's essentially when the electron configuration gets down to the noble gas core electrons. Okay. Oh, 6+. Okay. For nickel 2+, again, taking off 2 electrons, and we'll be left with 3d8 with one of the d electrons. So we'll have argon 3d9. Okay. Yes?
Are there any special cases with that where like you would use the orbitals first instead of the s orbitals?
I think that is mostly straightforward. Figure in your book, we're on slide 5 now, that has the common ions found in the metals, transition metals, number of transition metals. And so anything that's a yellowy orange color is a more frequently seen ion, and then the green is the less common ion. So there are many elements that have multiple oxidation states, multiple ions that could form. You don't need to be able to predict all of these, but you do need to be able to. So, I guess not for nickel and copper, my apologies. Not really. But for chromium, there was another option. I hate saying that there's no exceptions because there probably is, but I can't think of one off the top of my head. Some of these more frequently seen oxidation states result from different electrons leaving in different orders. We can delve into that later if you'd like, but in any case. So when we have partially filled d orbitals, those electrons are going to give rise to some interesting properties. The color of a compound and magnetic properties. We're going to really get into this towards the end of the chapter. I just want to leave it at this for now. We're going to have a demo Friday and on Monday that has some nice color compounds. We're going to talk about what's happening with those and why those colors are forming. So we have seen a little bit of transition metals before. If you recall, we had our complex ion formation in chapter 17, where that increased the solubility of slightly soluble salts. I want to bring this up again because we will be talking about many of these complex ions. And we will be thinking a little bit here about the magnitude of the formation constants. And that is important because it allows us to take advantage of certain properties of metals and how they form complexes. But before we get to that, let's do a few definitions. So complexes, that term simply means you have a central metal atom that's bonded to some other type of molecule or ion. So central metal atom bonded to group of molecules or ions. And in that case, an ion may be like chloride or fluoride. The molecules, there's a large variety that we'll see, but we've seen ones that include water and ammonia, cyanide, and things like that. So then the complex ion is the same thing, it's just that the overall, it has an overall charge. You also come across the term coordination compound. It's essentially the same thing, it's just another way of thinking about it. It's a central metal atom that has ligands bonded to it. So we're specifically using the term ligands. And I will say that ligands is also going to encompass all of the other possible things that are bound in, when we say group of molecules or ions. So the ligand is essentially just that, things that are bonded to the metal atom. Okay, so in our first equilibrium on this table, we have the silver ammonium complex ion. Ammonium in that case is the ligand. Our central metal atom is going to be silver. Ligand. Okay. And it is a complex ion because it has an overall positive charge. Make sense? Just some terminology. We've seen from our equilibrium constants, formation constants. So if we compare the complex formation of the silver ion with 2 ammonia versus the silver ion with 2 cyanide ion, you'll see that they both have very large formation constants, but the one with cyanide ion is very, very large. Okay, so that's going to occur to, that's if we made a mixture of silver with ammonia and cyanide, it would first form the cyanide, almost exclusively, because of how large that value is. So your book has hilarious, the tables are so silly. This chapter is really bizarre to me. There's like 3 different tables and they all say some common ligands, so I don't know why they just didn't make one big table. But this is the first table of common ligands that shows up. And you've seen a lot of these ligands in the formation constants from chapter 17. So we have water, ammonia, chloride ion, and cyanide ion. And these very easily form complexes with different metals. They have different binding strengths. Okay. We also need to recall molecular geometries. Okay. A lot of these won't come up in this chapter simply because transition metals don't form these geometries. The big ones that you'll need to recall are square planar, tetrahedral, and octahedral. Okay, so in square planar, we have a central metal atom. We'll just go with metals in this case. Central metal atom with 4 atoms bound to it. These could be ligands, okay? And they're all in one plane, okay? With tetrahedral, remember this one has the bond angles of 1 and 9.5, so it almost forms a triangle at the bottom with an atom pointing straight up on an axis. And then with octahedral, we're going to have bond angles between everything of 90 degrees. So 90 degrees here, 90 degrees here, etc. All right. So much of the work on geometries associated with transition metals came from Alfred Warner, who won the Nobel Prize in 1913, essentially for predicting or suggesting the octahedral geometry. And that came about in his paper in 1893, written in German, that is titled in English, The Contribution to the Constitution of Inorganic Compounds. It's actually a really long paper. This figure comes from it. This is trying to show an octahedral geometry. So there would be a central metal atom, and shows 5 ammonia molecules bonded, and then one, it could be something else that was listed as X. The main idea here was that he was proposing this octahedral geometry. I forgot to mention that all of this, he proposed this geometry before Lewis came up with his dot structures. So this is pre-Lewis dot. Okay, so it's pretty interesting the way this came about. Interesting. Sorry for the shadows. Okay. Werner was studying these 4 cobalt complexes. And so what he would do is mix different ratios of cobalt chloride with ammonia. And he would observe the color associated with those mixtures. So if he did a mole-to-mole ratio of 6:1, 6 ammonia to 1 cobalt chloride, he'd come up with a solution that was orange in color. If we reduced the amount of ammonia, he'd come up with a solution that was purple in color, and so on. An interesting thing that happened, though, when he had 4 equivalents of ammonia to 1 cobalt chloride, it ended up with 2 different color solutions. Okay, not exactly sure how he separated these out, but that is what happened. And so what he did then was he added to these solutions an excess amount of silver nitrate, he added silver nitrate, AgNO3. And he formed a precipitate, with the made silver chloride. And so he quantified the amount of silver chloride that was obtained. And for these different color solutions, except for the last 2, they were similar, they were the same. But you would get a different quantity of precipitate. And what that suggested was that the ammonia was coordinating with the cobalt in different ratios. So in the orange solution, found that there were 6 ammonia coordinated to the central cobalt atom, and so there were 3 chloride ion in solution. So this is essentially a salt right here. So the chlorides dissociate, much like NaCl, okay, and he could precipitate out the chloride. In the second one, he precipitated out less chloride because 5 of the ammonia were coordinated to the cobalt, but 1 of the chloride was now coordinated to the cobalt. And so that one does not precipitate out. Okay, so he was able to get these different, basically different precipitates, and able to figure out then the coordination chemistry, the coordinated bonds for the cobalt and the ammonia and chloride. Just an interesting way to do it. And I guess I shouldn't have that theory to work from. The formula, cobalt with 4 ammonia complex and 2 chloride complex. So let me write this. And that is, here's the cobalt complexes that have what he found, I don't know if this was the same paper, but it was found is that there's two different isomers that are formed in this cobalt complex. And we're going to talk a little bit more about isomers. But in this case, just know that it's a different arrangement of atoms bonded to the central cobalt atom. And you can see that on our what's called our cis isomer, the chlorides are adjacent to each other. And in the trans isomer, they're across from each other, across the metal center. Okay, so that's something that was kind of interesting that came out as well. In our structures here with the cobalt and the ammonia and the chloride, we're simply looking at the number of bonds between the metal and whatever it is that is bonded to us. So we don't actually count all the individual atoms that are bonded. I mean, we like the hydrogens on these ammonias, they don't count. But so in this case, the coordination number would be 6. Okay? For any octahedral compound. Another result of Werner's theory, Werner's work, was that he came up with a theory of valence. And what it stated is that a metal ion has a primary valence and a secondary valence. And what that means is that the primary valence is referred to as, more as we know, as the oxidation state. And the secondary valence is a coordination number. So we've seen oxidation state. Okay, that's, if you have an ion, that's the charge on the ion. We looked at oxidation numbers when we talked about electrochemistry in our electrochem review. That's the same thing. Okay. With coordination number, though, this is the number of atoms that are bonded to the central metal atom. Okay, so the coordination number is going to be 6. For anything tetrahedral or square planar, it's going to be 4. So the coordination number is relatively straightforward to determine. So we've seen a little bit with our formation constants of complex ions of how to write chemical formulas of coordination compounds. And so we are going to use square brackets, as we've been doing, to signify the coordination sphere. Okay, so the coordination sphere are the atoms that are, and ligands that are directly bonded to the central atom. This doesn't include any other atoms outside of the bracket. Okay, those ions are required essentially to make a salt, balance the charge. So, for instance, in our silver ammonia complex, okay, we've seen this written as a complex ion like this, but you couldn't actually buy that in a jar, for instance. You can't buy a charged species; it has to be balanced out. So you would get silver ammonia with it's a chloride salt, for instance, or some other halide. So whatever is written in the brackets, that's the coordination sphere. That's where the interesting stuff is going to happen. Everything else we pretty much ignore. Okay. The other thing to recall, this is back to chapter 16, is that when we take a central metal atom and combine it with a ligand, we essentially have acid-base chemistry. This is a Lewis acid-base interaction. And so we're forming a bond between the metal and some atom. Of course, this probably is obvious, but the metal complex is going to have different properties than the metal itself. So it may have different reduction potentials. So the silver in this complex might have a different reduction potential than the silver ion by itself. Okay? think that was the example your textbook used, but it also will have different colors in solution, things like that. And we'll also see, as I mentioned, that some ligands can displace others. So that also depends on the formation constants. Okay, so here's an example of some ligands being replaced. So our yellow solution is a solution of iron complexed with 6 water molecules. And what happens is this ammonia thiocyanate complex is added, an aqueous solution of that. And it's added in a relatively small amount. And what happens then is one of the water molecules in the coordination sphere is replaced by a thiocyanate ion. And we end up with a red solution. Okay? So you can see that by replacing one of the ligands, it drastically changes the color of the solution. And we'll see a little bit about why that is towards the end of the chapter. It's probably the more interesting part of the chapter, in my opinion, but okay, whatever. We'll get there. Okay, so thiocyanate is an interesting ligand in itself. It could bond to the central metal atom either on the nitrogen side or the sulfur side. So this is another way of getting an isomer, but I'm jumping. Let's go back to our iron complexes. So here we have iron complex to 6 water molecules, an overall charge of 3+. Again, let's figure out the charge on the metal and the coordination number. And everything here is, well, we'll figure out the geometry. All right, so what do we get for our coordination number? I'd like to start there. 6. Again, octahedral geometry. So what about the charge on iron? So we know that the overall charge on the complex ion has to be +3. What's the charge on water? 0. So the charge on iron has to be +3. Okay. All right, so then let's look at the thiocyanate substituted complex. Whoa, that's fun. How'd that happen? Okay, again, looking at charge on the metal, the coordination number, and the geometry. I'll go ahead and we can already write coordination number of 6 and octahedral. All right, right, so we have an overall +2 charge on our iron complex. So we're going to have iron plus 5 water plus the thiocyanate equals +2. Okay, we know water has a charge of 0. Thiocyanate has a charge of -1. Okay, so what does the charge on the iron have to be? What do we get? +3. Cool. All right, so we've seen a lot of octahedral complexes, 6 coordination number, but that's not always the case. And so we can have iron complex that is octahedral, has 6 fluoride bonded to it, and this will have an overall charge of -3. But the size of the ligand that is bonding does play a role in the number of ligands that can bind to it. Okay, so we have iron chloride that has 4 chlorides. Okay, so we have a different geometry, and actually I don't know if this is trigonal, if this is square planar or tetrahedral. We'd have to write out the Lewis structure, but we could do that, I suppose. But you could go through and figure out, again, charge, oxidation, coordination number, and geometry for these. Heavy again, sorry. I copied these tables right from a PowerPoint that came with the textbook, and that's real crappy. I apologize. That's what I get for being lazy. Okay, so let's think about the charge, coordination number, and then the geometry associated with some of the compounds we just saw. So determining the charge on the metal ion, that's on the metal only here, is probably the hardest part on this chart. The coordination number is going to be pretty straightforward, as will then the geometry. If you know the coordination number, you know the geometry. So the coordination number, again, is just the number of atoms that are bonded to the central metal atom. In our cobalt complex with 6 ammonia bonded to the cobalt, our coordination number will be 6. There's 6 total nitrogens bonded to that central cobalt atom. And because of that, that means the geometry is going to be octahedral. The charge is a little trickier to figure out, although you take it apart and do this sort of stepwise. So let's look at our cobalt complex and only look at the coordination sphere. All right, so let's take this one. We're going to do this. We're going to remove all of these chlorides that are outside of the coordination sphere. And they're chloride ions, right? So those all have a -1 charge. Since we're removing 3 of those, what should be the charge on the complex? +3, right? Okay, because when you have the chlorides associated there, the charge is neutral. Take away 3-, you need to have +3 for the complex ion. Okay, but I'm just interested in the charge on the metal center itself. So in this case, you need to know what the charges are on the ligands. There will be a few that, even though your table has 3 tables of common ligands, there are a few that will stick out. Okay, ammonia being one of them. I'm sure at this point we all know that our ammonia, NH3, doesn't have a charge associated with it. Okay, so if we were to ignore those ammonia, essentially take them off of our cobalt, we would be left with a 3+ charge. This is just like figuring out oxidation numbers. like we did in our electrochemistry. So if the overall charge on the ammonia is 3, but our complex ion has a +3 charge, that means that cobalt has to be contributing that +3 charge. Does that make sense? We'll do a bunch of these. All right, so work with your neighbor and figure out the remainder of these for on this table, and then we're going to do some additional ones as well. So figure out the coordination number, geometry, and charge on the metal. All right, so let's take a look at this second compound. Let's start with the coordination number. What do we end up with for the coordination number for the second cobalt compound? 6. All right, so there's 5 ammonia and 1 chloride bonded to the central metal atom, so a total of 6. Coordination number is 6. So what is our geometry? Octahedral. Whoa. Okay. What about the charge on the metal? So I'm going to rewrite this. I'm going to essentially remove these chloride ions that are not part of the coordination sphere. So we'll have cobalt, 5 ammonia, and a chloride. And it's going to have a, what charge? +2. Okay, so that means when we sum up the charges of the individual things inside the brackets, it has to equal +2. We know, I'm going to just write this in brackets here like this. Okay, so for our cobalt, that one's the one we're trying to figure out. So let's leave that blank. Our ammonia, 0. What about chloride? Yeah, -1, right? So chloride ion -1. And so what does that mean cobalt has to be? Got to be +3 in order to end up with the overall of +2, excuse me. And if you go through and do the remainder of these, this cis and trans isomers are going to be exactly the same as each other, and those also are the same as what's already written up here. So you should have +3 charge on the metal for everything, oxidation numbers of 6, and all octahedral geometries. So that wasn't so super exciting. Okay, let's keep going. That's the repeat. Okay. All right, so again, most common geometries that we need to worry about: tetrahedral, square planar, octahedral. These are going to be the main ones. So you can get a sense of the layout for those atoms, and that will play a role in some of the coordination chemistry that we'll see. Here's some more common ligands. So these are what are referred to as monodentate ligands, meaning they bind to the central metal atom in one spot. So I have they bind to a central metal atom via one atom. Okay, here's our thiocyanate, and there's an or written here. So if I zoom in, you can see that it can bind to either side, the sulfur or the nitrogen. That's what the or is referring to. Same with the nitrite ion. It can either bind to the central metal atom through an oxygen or a nitrogen. Okay. Those are sort of the less interesting ligands. The more interesting ones are those that are called chelating ligands. And there's a couple of categories. This top row of ligands are bidentate, meaning they bind to the central metal atom through 2 points on the ligand. So anywhere that there is a yellow sphere, that's where that atom will bond to the central metal atom. The other important thing on this table is the abbreviations. So ethylene diamine is a common ligand that you will come across. It's abbreviated EN, and I'll show you in a couple slides here how that bonds to a central metal atom. But both of these nitrogens will bond to a central metal. And then the polydentate, they can have 3 places in which they bond to a central metal atom or more. This is EDTA. You may have seen this abbreviation on your shampoo bottle or something like that. EDTA is in a lot of things. I think it's even in salad dressing. But basically what it does is it binds calcium and magnesium and keeps them from affecting other things in consumer goods. It's used also in chelation therapy. If a person has lead poisoning, I'll show you a little bit about that. But this has 6 points at which it binds to a central metal atom in that one molecule. So the 2 nitrogens that are sort of in the center, and then the 4 oxygen that are on the ends. And this figure represents EDTA bonding to the central metal atom. So it almost completely encircles that metal and holds it in place and sort of keeps it there, which is kind of neat. There are ways that you can quantify metals in solution using EDTA. It's actually an EDTA titration. People do this when they're testing hard water. If they want to figure out if they have how much calcium, how much magnesium. That's the old school way of doing it. It's through an EDTA titration. I don't think that many people do that anymore in real life. So this is our ethylene diamine ligand that is bound to a central cobalt atom. And there's 2 representations here. And this one showing all of the atoms that are present on those ligands. And so if I draw this here, this is one ligand, and it's binding to 2 spots on the octahedral geometry. This is a simpler way of writing that, and often when people are inorganic chemists are giving talks or presenting material in some way, and they want to show really complicated ligands but don't want to have to draw out every stinking atom, they'll just go like this, and there you go, there's your ligand. Okay, so just to show something in a relatively simple way. Okay. So again, notice the abbreviation. The whole name of this complex is tris ethylene diamine cobalt 3 chloride. Again, you should be very thankful we're not doing naming. Oh. Okay, well, I'm going to talk a little bit about this. So complexes that form with chelating ligands, so that's the bidentate or the polydentate, they tend to form more stable complexes than those formed from monodentate ligands. And you can do ligand exchange because of this. So here's a nickel complex with water. If you add an ammonia to that, you can actually replace the water with the ammonia and have a relatively good formation constant, 10 to the 9th. But you can also take that water and add ethylene diamine to that solution, like the nickel water complex, add ethylene diamine, and replace all 6 water with ethylene diamine. And that has a huge formation constant, 10 to the 17. Why would that be? Let me give you some clues here. So here's some the total molecules or things. There's 7 and 7. What happens to the entropy when we go from, oh, I'm totally messing this up. No, I'm not. Okay, so when we go from having the nickel water complex to then replacing those waters with ethylene diamine, what happens to the entropy? It increases. Okay, do you see that same increase with that first example? No, so we have, we replaced 6 water with 6 ammonia in that first example. So there's no change in entropy. But in the second example, we see a huge change in entropy because it's a larger number of molecules that end up on the product side. Just like when we saw with gaseous molecules, same reasoning goes in here. There's I do recommend that you read page 1001, a closer look. Okay. Talks a little bit more about this, gives you other thermodynamic properties as well. That's kind of interesting. Good reminders for chapter 18 or whatever it was.